I think I first met Pascal in person in Canberra. It was 2007. I think you were having sabbatical at that time, maybe. Yeah. So.
Not 2007.
2007. Yeah. I was there definitely 2007. So yeah. And at that time, actually, there were many people I see from this room. So I was a postdoc of Steve, and then so I was involved in a project with O'Shea. I mean Pascal with just a layer potential thing, and I had just one paper with Pascal. Okay, and I had to find some picture of Pascal, and this is.
I was expecting.
Yeah, this is. Yeah, do you remember this place, right?
Yeah.
I see some people here. Okay. And so it was like light hiking, I guess. Yeah, and it's not compared to this.
Yeah, the stairs were kind of steep, right?
All right. Okay, I'll just start my talk. Yeah. Okay, I'm going to talk about, before I actually talking about my result, I want to go back to this very classical actually problem, and I'll overview something. Actually, the Wolfgang actually Arendt was talking about the same topic, so I mean just, but anyway, I want to, it wouldn't be so bad to go over this kind of material again. Okay, so what is a classical Dirichlet problem? Dirichlet problem is you want to actually solve this Laplace equation with this data, right? And there's many ways, actually, I mean, various ways to solve the Dirichlet problem. And the first one I can see is from Green's method. And then there's Gauss actually used a single layer potential to solve this problem. And then there's the Kelvin and the Dirichlet actually use a variation method, and there's so-called Dirichlet principle, right, to solve this problem. And then, okay, so this is actually the Perron's method. Okay, Perron's method. I have to go this way, or so why is the anyway? Okay, and okay, let me just. Okay, let me begin with this Green's identity. Green's identity is it's nothing but just the integration by parts formula, right? If omega is smooth enough, then you have this nice identity. U times Laplace v minus v times Laplace u is represented by actually the boundary integral of those things. And then the Green introduced the so-called Green's function, which is nothing but, okay, you just have, you apply the Laplacian to Green's function, you get the direct delta, and the boundary value is 0. Then by formally putting the G into V, you're going to get this identity, right? Okay. So, and then actually the thing is, okay, Green actually assumed that there always exists a Green's function, but it's not really easy to. I mean, it's not kind of that obvious thing. But this is useful, really, when actually omega has simple geometry. For example, omega is a ball. Then you can, this becomes so-called Poisson kernel for the ball, and you have actually a solution. Okay, next thing. Then I introduced a little bit of concept of superharmonic function. As you know that the Laplace equation and just harmonic function is characterized by this mean value property, right? So you don't need to assume anything. As long as u is just like any continuous function. If it satisfies that this mean value inequality, then the u becomes harmonic. And then what is superharmonic function? Superharmonic function is, okay, you relax actually assumption a little bit, okay? Just you assume that just the function is a low semi-continuous function, which is not identically to infinity. And if you have this, if you satisfy this mean value inequality, then you call this function superharmonic function. And if you subharmonic is just you reverse this inequality, and you assume that U is low at the upper semi-continuous. Okay. And I want to actually remind you some of these properties of the superharmonic functions, which will be useful. So that, okay, if you have two functions of superharmonic, then their sum, and if you multiply the positive constant, it's also superharmonic. And the minimum of two superharmonic functions is also superharmonic. And then there's also a strong minimum principle. So it's not a strong maximum because it's just you are talking about superharmonic function. And there's a comparison principle. And the thing is, pasting lemma is just like you have two functions, right? For example, you have v, which is less than or equal to u in, say, smaller set, and the u is here. And if you take the define w like that, and if you know that the w is low semi-continuous on this boundary, then the w becomes superharmonic. All right, so then here comes the Perron's method, okay? So if you have superharmonic function, then you can define so-called actually harmonic lowering by defining that you are given any ball, small ball, inside of this omega, and you keep u as it is outside the ball, but inside the ball, you replace u by its Poisson integral, so that then it's called actually the harmonic lowering over u over v, and this is the property. Okay, it is less than or equal to u, and this is superharmonic using the pasting lemma, and it's harmonic in B. Okay, so here comes actually the thing. Okay, you have a collection of superharmonic functions f. We say actually that collection is saturated if those two properties hold. Okay, if u and v given, then the minimum of u and v is still in the family, and then this harmonic lowering of u is still in that same family. Then you take the infimum of u among this family and define this as a v, and as long as it doesn't take the value negative infinity, then this is harmonic. Okay, so that's how actually just a kind of a Perron solution actually comes up. So you just, this is my notation for superharmonic functions. Then, okay, you have all the superharmonic, you call this family F, set of all superharmonic functions, which is the boundary value, in this sense, is bigger than or equal to F on every point of boundary. So then you can easily see this set, this class F is saturated. So you can define actually, if you have just take the infimum of this V, okay? And then this, I want to call this as upper Perron solution, okay? So this is a solution in omega. And then, okay, I mean, you cannot really say actually boundary value is achieved, but I'm going to get to the point soon. And you can also define the lower Perron solution by actually taking the V to be subharmonic function, and you have this limits which is less than or equal to F on the boundary. Then that's called actually lower Perron solution. And then obviously, a lower Perron solution is less than or equal to upper Perron solution. Okay? Then there's actually a theorem due to Wiener. And if omega is just a bounded open set, and then two actual concepts of upper Perron solution and lower Perron solution actually coincide actually if the data is continuous. So you can just talk about the Perron solution. Okay? And this is the definition of regular boundary points. So boundary point is regular if and only if for every actually continuous data F, the Perron solution is the boundary value is achieved at that point. Okay? And there was another actually the characterization, I mean just the definition, characterization due to by a so-called barrier function. So if there exists a barrier function Q, which is superharmonic, and this becomes 0 at one point, x0, and it's positive everywhere on the boundary. If you have this barrier, then just that x0 becomes a regular point, okay? And of course, it's just if and only if condition, because if you have a regular point, by this definition, you can construct a barrier, right? By taking the boundary value of this, just a continuous function which vanishes at a single point. Anyway, so, okay, there's examples of a regular boundary point. So this, the first one is like introduced by Poincaré, and the condition is so-called exterior sphere condition, meaning that you can just touch, you can put a ball outside, right? And it touched at the boundary at a single point. Then this is a regular point. And not only this one, actually, there's tons of regular point. For example, so Lebesgue actually noticed that if you have actually domain can be like under this, like this is like what? Just a power function, right? Okay? So it's like so cusp is allowed. Okay? And especially when m equals 1, so this is this condition is so-called the Zarembas criterion, or it's like existence. It's called sometimes it's often called actually exterior Kohn condition. So if it satisfies exterior Kohn condition, that's a regular point. But not every point is regular. And the first one is again just observed by Zaremba. This is not actually kind of I mean, if you have just a disk and the origin removed, so then this is not this is isolated boundary point, and then this is not a regular point. But this is isolated. But Lebesgue actually gave an example of this the function which is called the Lebesgue spine. Okay, so I'm going to show you the picture of this domain showed here. So this is actually I took it from the paper 1925 paper by Urizon. So this was he died actually 1924 in France, and the cause of death is drowning. Okay, so that's why I didn't go to water yesterday. I know that the French show is dangerous. Okay, so this is okay the picture exactly like this. It's very sharp. Okay, so this point is not regular. Okay, so now I just let me quickly introduce the capacity. Capacity is okay. Suppose actually omega is a smooth boundary. Okay, so maybe I draw a picture somewhere. I don't see any chalk. Shall we over there?
You can use the other bone.
Oh, over there, okay.
Notice everyone, I didn't do my job, but there's something important reading here.
Okay, just. Suppose you have, say, omega. Okay? So smooth boundary. What happens is you are looking at the exterior domain. You put the boundary value u equals 1 on this set, and then the vanishes at infinity. Okay? And the harmonic, think about the harmonic function having this property. Okay, then so if you take this integral over here, so that's defined. It's called the capacity. Actually, it's called conductor potential. Okay, U is called the conductor potential, and this is called the capacity. Okay, and then it's just if you notice this, okay, this quantity, because U is supposed to be 1 here, all right? You multiply U, same thing, and then you can do this integration by parts over there, all right? Okay, and you get this is gone because Laplace U equals 0, so you end up with this. So this quantity is the same as that Dirichlet integral of U potential outside of this this omega. Okay, so that's potential. I mean, yeah, and that gives you actually one actually way to defining potential like that. So capacity like this. This one actually is I copied this from that book of Gilbert-Trodinger. Okay, I mean, it makes sense. Okay, you think about this function, compactly supported function, which is at least once differentiable. And then V equals 1 on K. And you minimize this energy, right? Then if you think about the Dirichlet principle, then there should be 0 outside of this omega. And then by this requirement, so V equals 1. And because of this identity I show you, so this makes sense, right? So you can define capacity in terms of this integral, Dirichlet integral. And here comes the famous actually Wiener's test. Okay. So for any gamma between 0 and 1, you define a compact set like this is shell analysis. And then this exterior of this domain omega. And then you compute the capacity and divide this by lambda to the k. So this actually goes, it becomes like, it blows up and this gets small, right? But if this sum is infinity, so that is regular. This is the if and only if condition. Okay. So in the previous actually Wolfgang's talk, you don't need to have this. It's the same actually. You can define CK as without this. You're gonna get the same actual characterization anyway. So it's just simple to see that. Okay, so this is Wiener's test, and this is kind of important because it gives if and only if condition, right? All right. Okay. Then, all right. Then I'm going to talk about a little bit about this capacitory potential, which is actually characterized just in terms of purely in terms of like a superharmonic function. I'm going to define U of E like this. You this V is among these non-negative superharmonic functions, and assuming that the V is bigger than or equal to 1 in E, you take the infimum of these superharmonic functions, okay? Then, yeah, this is, and you need a little bit of the thing actually. If you take the infimum of this, then it is not necessarily actually lower semi-continuous. So you take the lower semi-continuous regularization like this, and then this is called actually capacity potential of E, okay? So basically you can think about, if you think about the parent solution, so U is 1 on the boundary, and this is harmonic outside, really, again. So then the property of the potential, capacity potential is this, and it's between 0 and 1, and the interior is just 1, and in the outside of this set, actually that becomes a harmonic, and totally this is superharmonic. So that's how you actually characterize actually capacity potential, okay? Then, okay, there's concept of capacity measure. So if K is any compact set, then this is a theorem really. There is actually Borel measure, actually Radon measure, actually supported on this boundary of this compact set, such that this capacity potential, the potential is expressed as that's the integral against the Green's function. And then the measure is totally supported on this boundary, okay? And this measure is called actually capacity potential. And this is a consequence of so-called rigid decomposition theorem, okay? And I'm gonna explain this in a very simple term, really. So why this is true. So, okay, it's a simple observation. So U is a superharmonic is, this is if and only if so Laplace U is less than or equal to 0 in the sense of distribution, okay? If you have that, so then what you can do is, okay, you have your test function, the negative test function, then think about this one, I of phi. So this is non-negative, meaning that this is the distribution, which is non-negative distribution, meaning that it should be measured like this, right? So I of phi, this one is equal to this. There is a measure. Then, okay, suppose you can take the Green function into phi, like that, okay? And then from here, you're gonna get this one, so this direct delta. So your y goes up, and then your y becomes actually the integral of the Green's function against this measure, right? So of course, I'm a little bit cheating because phi is not really compared to the supported actually function. But you can do it like, for example, first you can take the Green's function, not the Green's function, approximate Green's function, which is like a solution of with the right-hand side, not the direct measure, but like approximate identity. Then it's regular. And for example, also you can multiply the Cordova function and make just approximation. Then you make this thing to be true, assuming that like u is like something like bounded. Okay. So in particular, actually, the capacity potential is like a bounded function. That's definitely a bounded function. So you have this representation, really simple. And then you can also check that this is supported on the boundary of the K. And then again, this is because, now notice this. So the measure evaluate the K, because this is 1, this is 1 on K is equal to that. So because actually this, you can extend this to the entire set because V is just supported on this boundary of K, all right? And then this one, you can just pretend that you can put the UK here. Then you're gonna have that. And you can pretend that you can do the integration by part again. You end up with this, okay? All right, okay. So that's one thing I wanna share. Okay, then let me move to this elliptic equations in divergence form. If you have the elliptic equation in the divergence form with the boundary measurable coefficients with a uniform elliptic condition, then there is a famous theorem by Littmann, Stampaccia, and Weinberger saying that regular point of this L is exactly same as regular point of the Laplace operator. So there's equivalence, okay? So, okay, how do they actually do that? Actually, they actually constructed the Green's function, first of all. And they actually established this pointwise bound of Green's function. And then you can have, okay, now think about that. All right, so you want to actually, okay, you just want to minimize this quantity among this order actually like, first we actually fix a ball, and you think about the sublight function, and which is bigger than or equal to 1 on the certain set E. And under this restriction, and you look for the minimizer of this problem. If you think about the A's identity, it's exactly the same thing, right? Like finding the potential there, right? So it's well known, actually, there's a theory, for example, if you see the book of Candelella and the Stampaccia, then there's a variational inequality, actually, characterization of this. So this can be viewed as the obstacle problem, right? And this can be actually, you have this variational inequality, okay? If there is a minimizer, this solution to this inequality, this problem, and you satisfy this condition, all right? So for example, so you can take the test function v, which is positive on E, then you have that. And this is, again, you can see that. So this gives you measure, all right? So by, again, Ritz representation theorem, you have this, there exists a measure so that actually this equality holds for that view, okay? Then again, you can take you can, again, just by using some approximation, you can take phi to be this Green's function. Yeah, then from here you get the u, y, and you get this representation, okay? So capacity now of E with respect to operator L can be defined like this one. This u, which is the minimizer, and you have this integral, okay? And this is defined with the capacity of E. And this agrees with the capacity of this for the Laplace operator, right? I mean, except that you are talking about the ball, not the entire set. But that's just a minor point, anyway. All right. So the thing actually I have to say that in the Littmann-Stampacher-Weinberger paper, they assume that A is symmetric. Okay, but that condition can be removed. And there's a paper by the Groth and Wiedemann without assuming the a symmetry, but you have to assume that the A is bounded anyway. So then what they proved is here among they proved this actually. Capacity of L is comparable to the capacity with respect to Laplace operator. And then, so you have this theorem. Again, they reproduce the Littmann-Stampacher-Weinberger result without assuming that the symmetry of A. Okay? So again, here, just the key ingredient is that a pointwise bound for Green's function, and then representation for this capacity potential. Okay, so if you have that, then basically you can follow the proof of Wiener really to get this equivalence thing. Okay, so now let me move to elliptic operator in non-divergence form, which is the main actually topic of today's talk. Now just think about this elliptic operator. Okay, it's in non-divergence form, trace of A of Hessian of U, and assume that they are uniformly elliptic. Okay. Then the question is, can you solve this Dirichlet problem? And then, okay, the next question is, the regular boundary point of L is the regular point of Laplacian and vice versa. Okay, so these are questions actually. And there was, of course, people studied this problem. Oleinik showed that the regular point for this operator L is equivalent to regular point for the Laplacian under the assumption that the coefficient A is C3 alpha. Then this is Hervé. I hope I pronounced that name correctly. Hervé. I think she was French, definitely. She actually proved that A is harder if she said actually this A is Lipschitz, but if you see actually I haven't actually, but according to Kirchhoff, actually this is she actually assumed A is Holder continuous. Then you have equivalence. Then later actually Kirchhoff actually reduced that this kind of assumption to the it's just A is uniformly linear continuous, then you have equivalence of the regular points. But even if A is continuous, you don't have equivalence really. In the 1970s, actually K. Miller actually first showed the example of that regular point for L is not regular for the Laplacian. And then the other direction was kind of, I think this was the first one actually, they showed this. They provide actually example of the example which is of the operator with the continuous coefficient. It's regular. The boundary point is regular for the Laplacian, but that is not regular for the L. Okay. So so that continuity is not really enough to have the equivalence. Then there was actually a paper, very nice paper by Patricia Baumann. She gave actually a Wiener test type of criterion for the regular boundary points for this operator L with the continuous coefficients. But that doesn't say much about the equivalence of the regular boundary points. Okay, because that Wiener criterion is expressed in terms of capacity, which is and some kind of with some weight, really, derived from that. So it's just the coefficients. Okay, now, let me explain our main result. So before that, I have to introduce this concept of the Dini-Mean oscillation. Before I introduce the Dini-Mean oscillation, what is Dini continuity? Uniform Dini continuity is this. This is oscillation function of f at scalar r, okay? So you take all the possible difference, right? As long as x and minus y is less than or equal to r, you take the supremum. This is called the oscillation of f. And then if this satisfies the so-called Dini condition, if this is finite, so then this is called actually a Dini continuous. For example, if f is a C alpha, Holder continuous, then oscillation is like r to the alpha divided r integrate. Of course, it's finite, right? So Holder continuous coefficient is Dini. But you have something like some function like 1 over log x squared, okay? So that's that is not Holder, but that becomes Dini. So Dini continuity is a little bit more general than Holder continuity. Then I'm going to define this Dini mean oscillation condition. So this is a mean oscillation function, okay? So I think everybody in this room knows about this mean oscillation, right? And then if this mean oscillation is satisfy this Dini condition, then I'm going to call this Dini mean oscillation or Dini MO. All right, so what's good for? What do you have? Nice. Okay, before that, I want to just say a few remarks regarding this DMO condition. Okay, so for simplicity, suppose f is a function defined on the entire set, and think about this mean oscillation function. Okay, if this is as a function of r, if this is just L infinity, then this is nothing but the BMO, right? Jones-Nirenberg space, and Olli was pointing out that it should be really the Jones-Nirenberg inequality, but I'm going to call it the Jones-Nirenberg. Okay. Anyway, then so if you take the supremum up to r and let r go to 0, then you know that this is so-called vanishing mean oscillation, VMO condition. Okay. Then there was actually very famous theorem due to Campanato. If this mean oscillation is like a power and is in this range, then this is equivalent to that f is a Holder continuous, really. That's equivalence, really. But if you have come down to this range, and if you go down to this Dini condition, then we do have example here. So this is, for example, this is Dini continuous. It's not Dini continuous, because if gamma is bigger than 1, so this is Dini continuous. But in this range, it's not Dini continuous. But if you think about Dini mean oscillation, then you kind of lose power 1, and this is integrable. So there's an example of this. So this is a kind of hierarchy. So Holder continuous. Double Dini continuous means, okay, so this, okay, let me just write it down. So you just send r to, say, 0 to r of, say, omega s over s ds. And this is a function of r, right? Okay, if this is Dini, then it's called double Dini. So for example, so if omega is like a power, then it's stable, okay? If you carry out this integration, all right, you lose power and you gain power, and again, right? So it's kind of this is very nice space, really. Okay, so and that's actually everything about really kind of the key point in the shadow theory. But if you start with the Dini function and you carry out this like a shadow type estimate, you don't end up with the Dini continuous function. You don't. If you start with double Dini function, you end up with Dini continuous function. So anyway, that is double Dini condition. So then it's a proper subset of Dini continuous function and the Dini MO. And you can prove that the Dini MO is uniformly continuous. Okay, and this VMO and the BMO. So that is a hierarchy. All right, so let me actually, there was a theorem I proved actually 7 years, maybe it's 8 years ago, with Hong Jiedong. So we have some result, but let me state this, first state this problem. If you have non-divergence type equation, right? So this one L equal F, and assume that A and F, both coefficients and the data are linear MO, then this W21 solution is C2. It's really continuous differentiable. It's kind of, what you do is you push the Schroeder theory up to the limit, actually, in some sense. Okay? So then you have corresponding result for C1 and C0. I mean, this double difference form equation is like so that is nothing but what's the adjoint of actually the non-difference form operator. So you have Dij, Aij times U. So operator like this is called a double divergence form operator. Okay? So yeah. So then you have C0 result for this double difference form operator. So that is crucial to having this pointwise bound for this Green's function for non-difference form operator. Okay? So if you have like a divergence form operator, then each adjoint is also divergence form. Okay? But if you start with a non-difference form operator, its adjoint is double divergence. And the thing is, okay, if you have this operator, this is not bad. This is a pretty bad operator. For example, if in the one dimension, you have AU, okay, and the double prime equals 0. Think about this equation. So this means that AU is what? Just linear function, right? So if A is bad, you don't get much, really, right? There's no improvement of regularity at all. So, and if you have, say, if A is just continuous here, and the solution to this equation is not necessarily actually bounded. So you do need some kind of more restriction. And then this is the weakest actually thing you can get. So if you assume the DNMO, you can get it, C0 regularity. And that helps you to get this Green function bound. Okay, and yeah, actually, this is in the two dimension. Actually, you have logarithmic bound. You can show that the Green function is what the BMO function. So you have low function, and that result was obtained by actually me and Hongjae a few years later. Okay, then now I'm gonna just state the main theorem and a quick proof, I guess. Not proof, let me sketch a proof. Okay, I consider the operator like this. L of U is this one, general actually non-difference form operator. I will assume that A is symmetric and it's uniformly elliptic, and A is a DNMO. And for B and C, I allow them to be singular, but B is in LP and C is in LP over 2 for some P bigger than D. Okay, and I assume C is less than or equal to 0. And I mean, you can relax this condition a little bit, but anyways, I want actually maximum principle to hold. Okay, so then this is the result. Okay, so okay, under that assumption, regular point for this L is the same as the regular point for the Laplacian. So yeah, that's the main result. And I'm gonna just remaining 10 minutes, I guess I'm gonna just quickly go over the proof. Okay. Okay, so this is a corollary. Because of this solvability, I mean, you can see that if regular domain means, okay, is every boundary point is regular, then for any function, continuous function, you can solve this problem here in this class, W2P here. You can solve this Dirichlet problem. And then in particular, that gives you some actually more refined result for the Green's function. If you have omega to be just a regular domain, then you can construct the Green's function, and you can have this bound. So previously, this result was obtained for only C11, but how you can move from C11 to D? Because if you have a large ball, C11 domain, you have Green's function, then that is continuous, right, inside. You solve that you just take this boundary value for that Green's function and solve the problem, so Dirichlet problem. So you can get this Green's function, and you're gonna have the same estimate. All right, so okay.
A is DMO again?
Yeah, DMO. Yeah, here everything is a DMO. Yeah. So under the same assumption. Yeah, it's just corollary of the same paper. Okay, I'm going to tell you a little bit about just the idea. I mean, so this is a kind of a common trick in the PDE. You have C, you don't like C, you want to get rid of C, okay? So what you can do is, okay, what is going on? Oh, I have to go back. Okay, I see. All right. So then, okay, this is a lemma. Of course, you have to prove this. You can have some function zeta, okay, which is 1 on this boundary and satisfying the equation. Then what you can do is, okay, you can prove that zeta is strictly positive inside, and you have this estimate, okay? And then the zeta times v, u solves this, okay, this, okay, if you add of u, just calculus, end up with zeta times this operator, L tilde of v. So this L tilde doesn't have C. C is gone because of this. And then B tilde is this one. And then this has low bound, and then this is here. So this is in LP. So it's in the same class. Okay? So what you can see is, okay, solving this Dirichlet problem, and of course this is also continuous because we assume the P is bigger than D. Like from the overlap embedding, you can see that this is continuous, right? So solving this Dirichlet problem is exactly equivalent to solving this modified Dirichlet problem for this modified operator, L tilde without C. Okay? And then just the zeta is strictly positive, it plays a role here. So this way you can get rid of C, okay? So that's a well-known technique in the PDE. All right. Then you can, what you have a solidity in a ball. You can solve Dirichlet problem in a ball. You can find solution. Okay, this is the P, okay? Of this, you can solve this with the maximum principle. And that gives you actually existence of so-called L harmonic measure. Okay? So now what you have is you have solvability in a ball. You have concept of super solution and everything. You can run the pattern process, really. So you can construct a pattern solution in omega. Okay? So for this actually scenario, you don't really need DNI-MO condition. VMO is enough to get this because I'm relying just using the W2P solvability. Okay? So up to here, you don't need anything. Okay? I mean, except that, say the VMO condition, or just a small, actually, the VMO norm. So anyway. So then, okay, now you have to, say with the Green's function. So the Green's function is okay. You can actually construct Green's function again in a ball. Okay? There's a low order terms, but you can actually handle that. And what you can do is, okay, you have upper bound here. Upper bound is valid. And the lower bound, you should be stay away from the boundary, right? So if you stay away from the boundary, you have also lower bound. Okay? So for that, actually, we strongly use the assumption A is DMO. And by the way, this result is available for the divergence form equation under the mere assumption that A is bounded and measurable. Yes, measurable, yeah. Okay. All right, so you have that. And the next thing is, okay. Now recall this, okay, this so-called capacitor potential. So you have set E, given set E. You think about all the non-negative superharmonic function, L superharmonic function, okay, which is bigger than or equal to 1. You take the infimum, and you take the regularization of this, so that actually this becomes a lower semi-continuous. Then I claim that that potential can be represented as the integral against a certain measure, which is supported on the boundary. And I define the capacity like that. Okay? So this is mostly actually a kind of, I'm going to explain this a little bit here. So this is not really clear, okay? Because if you think about in the difference form equation, you have a variational characterization and you have a variational inequality. You have you get the existence of measure for free, almost for free. For the non-divergence, for the Laplacian it's okay because the Laplace operator is special, right? Laplace operator is a superharmonic if and only if there's a distributionally superharmonic. But that uses actually mean value actually. Just you modify the superharmonic function with like a radially symmetric function, and then that's how you get that property. But that is not really easily available for the non-divergence form operator. So what do you do? Okay, I borrow some idea from the abstract potential theory. Okay, suppose this. Suppose there is such mu, and you can represent actually non-negative super solution like this. Okay, you don't know what that measure mu is, right? But suppose, okay, you have this one. Okay, how do you know the measure? If you know the value of measure on every, say, open sets, then you're okay, right? Because this measure is supposed to be a regular measure. So how do you do that? Okay, I'm gonna integrate this here on this set. Okay, this is D and that's B, okay? So I'm gonna define this as UD. And this gives the decomposition of U as a UD plus UD prime. So what happens? Okay, they are both non-negative super solutions, okay? And so if you have this one, you are away from this set, D, it becomes a solution, all right? Because that's supported. You're actually cutting this at the level of D. And then the rest, which is U minus UD prime, satisfies actually this equation inside of D. And there is a certain sense of maximality because you are using this one characteristic function. You cut the two functions as like a sum of two functions, right? Which is supported there and there. There's some sense of maximality. And that can be characterized this, like that. So this is 1, 2, 3. That's assuming there is a mu, then you get this property 1, 2, 3. But if you think about it, this gives actually some kind of characterization. You are given U, you are given D, right? And if you have actually decomposition like that, then you are good, right? So this can be done without, this is due to Rosemary Hervé. Actually, this is written in French. It's a very long paper, you know. I mean, it's just I was intimidated to read this, but yeah, I mean, I was actually kind of looking for something like this in the paper. Written in French, my French is limited, but with the help of ChatGPT, I could locate actually this specific thing. What you can do is, okay, so you have a superharmonic function. It's abstract potential theory. There's no actually the idea of just differentiation whatsoever. So if you have a concept of superharmonic function, and okay, you have open set, then you just collect this kind of family. Okay, non-negative actually superharmonic function, and the U is given, and then V minus U is like a superharmonic in D, and take the infimum. Okay, I call this is well defined. Then this projection type of thing is exactly that UD in the previous slide. Okay? So you are given superharmonic function, and you are given any open set D. You can decompose U as a UD plus UD prime, and the UD is nothing but like you're integrating your measure on this set, characteristics on this set D. All right? Then having that, okay, you can easily see that okay, I'm gonna wrap up soon. Existence of measure is kind of obvious of this property, really. Okay, so you get the measure for free, but there's one problem. Okay, this is what we have. Okay, there exists a family of measures for every open set D here. this can be represented as this function, projection of this potential on this D is this. And but this part is easy. You can show this is supported in K. But how do you relate this with that one? So that's a little bit problem because this is dependent on X and there's X, right? Supposedly this is may depend on X. That is not good. But the thing is, the nice thing is this. If you look at this one, PBR of this one, what this is a kind of projection of this function on BR. So you are away from BR, that is a solution. Suppose you are shrinking R to a point, what it becomes? It becomes like a solution away from a single point, right? So you can prove that is a Green's function, really. And you normalize like this, then this is, limit of this is really Green's function. Okay, so using some kind of PD technique, you can prove that. So you have that. And there's, you can think this is Radon-Nikodym theorem. You define this as a d mu. And then it doesn't depend on X, really, now. So, okay, so that's how you end up with this representation formula. You found a measure mu such that this potential is written like that. So that's it. If you have that, and you can run this machinery of this Grudem-Wiedemann, you can get the result. So, okay, that's it.